So has it started recording yet? Okay, right. So before I will carry on with the example. Okay, so we had for part A, right? Part A. For part A, we have moment about the z-axis, right? So given the moment about z-axis, we applied the formula where stress x is equal to mz over izz multiplied by y. Okay, so we have that. So we found out 2 points, right? We found 2 points. Okay, we found that we drew a structure like this, right? And then on top we call alpha, below we call beta, and just to recap, we calculated that stress x. I'll write somewhere more. So stress x alpha, we got it as, is it tensile? I'm trying. Yep, it is tensile by, what was it? I can't remember now. 75. Then we calculate stress x at point beta, and we realize that it's minus 75 times 10 to the power 6 Pascal. So what I'm going to do now is I'm going to sketch the normal stress distribution. Okay, so we're going to sketch. So on this sketch, I'm going to change my view. Is that I can't see my cursor now because I've toned down my, hold on. So we are going to okay. So we're going to draw this. I'll redraw my. I'll draw it relative to the boxes. Okay, so this is point alpha. That is point beta. Okay, so we know that this is our centroid or neutral axis. For this case, I'll call it neutral axis first. Okay, because we've been using the term a lot. So that is our neutral axis. Right. Then this is our y. Right. So this is our y. And over here, this is our normal stress. All right. In the x direction. Right. That's our normal stress in the x direction. So at alpha point, right, where y is positive. So y is positive. So this is our alpha position. And this is where our beta position is. Right. And we realize that stress x alpha is tensile by 75. So I'm going to declare this my 75. Over here will be minus 75. So we can draw a line now, right? And then it will come to here, right? So it intersect exactly at the center. So now to sketch this, okay, so this is our what? Our 75. And in terms of height, I think it's 0.01. Okay, over here is our minus 75 and minus 0.01. So that's how you label. Okay, so if you don't want to draw the arrow, I'm fine. Okay, but I'm going to draw the arrow for you guys. So at alpha is going to be tensile. So y is on the y-axis is where the material is. Okay, so it pulls itself out, tensile. Okay, and then at beta is compression. So from here it pushed towards the material. So that's compression. Okay. So this is how your stress your stress X distribution look like due to bending moment. Okay, so now if we look at B now, okay, so if we look at B, now B is about the MY axis, right? We still calculate stress. Okay, I elaborate again. We still are calculating stress X. Now it is equal to what? My over Iyy multiplied by Z. Okay, and then we label them. So I'm still going to draw the same way. So if I were to draw my transformation on the left one, so this is my X. I'm sorry, that is my Y, and this is my Z. Okay, so I'm not going to change. Okay, so I'm still going to draw the same diagram. So again, my orientation on this one. So this is my Y. There's my Z. Okay, same diagram over here. However, the interest is different now. Okay, so we caught one point. Let me look in the previous slide. Which one is I and which one is J? I forget. Okay, so this is point J. All right, this is point J, and this is our point I. Right, and then we calculated, right? We say point I, stress X in the I direction, right? In the I direction, stress X in the I direction is equal to I'm trying to recall now. Point I is in compression. Correct me if I'm wrong. Okay, anyone? Am I right? And then stress I in the J. So this one will be equal to positive 125 times 10 to the power 6 Pascal. So we are going to sketch again. Okay, so now everything is in the Z direction, right? So I'm going to sketch down here. So now what we are drawing is in the Z direction. Okay, so again, I'm going to draw it. You all can see, yep. So over here, this axis over here, right, is still my stress X axis. No, this is not my stress. I can't. Can I call it my? No, this will become my Y axis. So the Y axis will flip because we're going to do it relative to our structure. Okay, so this is our Z. Okay, then over here, this is our stress X. Okay, so this is our stress X. Okay, so this is our stress X. So from here, we are going to sketch. So we know that X is going to be 125. So over here, these are both my 125. So this is 125 tension. Over here, this is my minus 125. So J is in tensile. Okay, so J is in tensile over here, right? Let me see. J is J in tensile. Wait, let me J is J. Yep, J is in tensile. Okay. And then I is in compression. Okay, I is in compression. So you draw a straight line. Okay. So in terms of stresses, okay, so in tensile, everything is pushed. Sorry, I'll put over here 125. Okay, so this one, everything is in tension. Right? Everything down here is in compression. So it's pushing towards the Z-axis is in compression. Okay. So this is how the shear force and this is how the stress distribution will look like. Okay. Now, the next thing I want to elaborate, what do we mean? Okay, what do we mean by symmetrical bending? So all this we see over here, right? All these are symmetrical bending. Okay, so on the problem at A, the symmetrical is alpha and beta, so the stress are the same. Okay, at B, I and J are the same. Okay, so we call it symmetry. Okay, so but what do we actually mean by symmetrical bending? Okay, what do we actually mean by that? So initially, I thought symmetrical bending is based on geometry and loading, which is wrong. Okay, so now I'm going to highlight what do we mean. Okay, before we go for the next example, what is, oh, before that, anyone, any questions regarding the shear force, the bending moment stress or the normal stress distribution? Anyone, any questions so far? No, I don't see any questions. No one raised any any concern. Okay, that maybe it will take time, then you will come into anyone. So I have someone putting up your hand. Yes.
Professor, why is the direction of the stress x should be y?
No, that is still the x direction stress. Okay, the stress is still in the x direction. We're not calculating stresses in the y direction at all.
I see. Okay. Thank you.
Okay, we are not. So we are still all calculating stresses in the x direction. The bending stress are all still in the x direction. Okay. I know why you asked that question, because all of a sudden I flipped the axis down here, right? Now this is Z, and then over here is my stress x direction. Yes or no?
Yes.
Yeah. So if I were to do this, okay, you will not be. If I were to take the whole thing, okay, if I would take the whole thing, right, and I hold on, hopefully it will not crash. Yeah, hopefully. If I take the whole thing, I copy, okay, and then I paste as picture, and then now if I rotate it this way, can I rotate? Yeah, I think I can rotate towards the right. Okay, so now you see everything is the same now. Yes or no? If I rotate this way, you will not have that question, right? Okay. So everything we still calculate in the what? In the x direction. Okay, in terms of stresses. Does that make sense to you or no?
Thank you.
You okay?
Thank you.
Okay. Right. So now, why do we call all this symmetrical bending? Okay, what is symmetrical bending? Okay, so a lot of times I thought symmetrical bending has to do with the geometry and how the force is loading. Okay, so let me elaborate what do I mean. Okay, so what is symmetrical bending? Okay, so what do we mean by symmetrical bending? Okay, so if we have a structure, if we have a structure, okay, now let's say we have a structure. Okay, so this is point A. Over here is our point B. Now our structure is loaded differently. Okay, our structure is loaded this way. We have an evenly distributed load. So this is our omega. Then we have a force down here, P1, another force down here, P2. Okay, so based on geometry or transformation, X, Y, this is our rotation about Z. Okay, so you know for this case, the structure is not loaded symmetrically, yes or no? Right? The example before, okay, or when we started, right, we realized that, hey, this is symmetrical, right? Symmetrical about the y-y axis in terms of loading, right? The geometry, left relative from point B, left and right are the same, right? From point B, right? Left and right are the same. The distance are the same. Is this the definition of symmetrical bending? The answer is no. Okay. The answer is no. So for this case over here, the one that we're just drawn, it is not symmetrical about anywhere between point A and point B. Yes, right? It's not. On one side you